Ernesto and Ricardo. I think it's an excellent idea that's needed to follow in this pandemic situation. Well, I think all people may see my first slide.
Yes.
Yes, we can see your face.
The question now, I will close the video. Yesterday, I have some problems with the internet, and I prefer to close the video to avoid problems. Okay, I will close.
It's fine, it's okay.
My video. I maintain the microphone, and don't forget the microphone, and I will start now the presentation.
Okay.
Well, as you can see in this first slide, I am going to talk about water and wastewater treatment by ozonation. The presentation will be recorded. That means all the information you will have later. And if more information you want, here are all the important information around Professor in Chemical Engineering, Analytical Chemistry Department, University of Barcelona. And this is my personal address, santi.esplugas@ub.edu. Now, okay, yes, this is the second slide. Well, this is more or less the outline of the presentation. I will start with an introduction about ozone and the relation of the ozone with AOPs. And one important aspect about ozone generation, but it's easy to generate ozone, but it needs a lot of improvement, by science and technological people. Later on, I will focus in this webinar in water and wastewater treatment by ozone. I will talk generalities about water and wastewater characteristics, mainly physiochemical characteristics. Later on, I am in a chemical engineering department, and we develop a lot of experiments at lab scale, pilot plant scale, and I participate in SOP demonstration experiment, that means almost large scale. That means I point these points that are very interesting about modeling of the ozonation, mainly in the mass transfer path. Some important parameters not normally used in the lab. Have immediate ozone demand, IOD, transfer ozone dose, and kinetics constant. The first K, the capital K, A is the mass transfer kinetic constant, and KD are the kinetics of reaction of ozone with other pollutants. I will talk something about one aspect that sometimes the people in the lab forgot. It's the changes in the water matrix. It's important. Almost people are more focused in the pollutant removal because it's maybe is the most important problem. But don't forget the changes in the water matrix also. And finally, I will talk about something it's more or less already new. I think it started in 2017 from people from the IABAC in Switzerland, Zurich. It's about to work in hydroxyl radical exposure and ozone exposure in order to try to control and to predict some situations working with ozone. And finally, I will draw some conclusions about my presentation. It will be a generalist presentation with some specific slides managing some experimentation. Well, let's talk on ozone. Ozone, this is a chemistry. This is nice molecule with 3 atoms of oxygen. And here is more or less the history of the ozone. Really, the ozone comes from the ozane. It's a smell in Greek. This is because if you are in a storm night and there are some sparks in the sky, you will smell something, and this normally is the smell typical of the ozone is formed by the sparks and the oxygen present in the atmosphere. And as you could see, practically ozone was discovered 200 years ago, more than 200 years ago. No, near 200 years ago, and only in 1873 it was known that the molecule was the same that the oxygen and is formed by three atoms of oxygen. It's important, two important characteristics of the ozone. One is this, I will focus more in the next slide on this, is for one part we have the tropospheric ozone. When you go to the media, you will see people talk about the good ozone and the bad ozone. The good ozone is the stratospheric, is in the stratosphere, and adds it an ultraviolet filter of the radiation, and prevents that the UV radiation arrives to the surface of the Earth, mainly in the southern hemisphere. That is the good ozone, the stratospheric. And the tropospheric is the opposite, it's the contaminant. It's a measure of the contamination of the air, and it's important mainly in the cities, and it corresponds mainly part to a smoke photochemistry, action of the light, ozone, combustion of the cars. It's a very complex system. Well, and finally, another important characteristic is that one, is thermally unstable. And this is a characteristic that has his advantage and his drawbacks. He has to produce in situ. Has to produce in situ means that you need to produce in situ. It is difficult to store it, impossible to store it. Almost has a problem of explosion if you have a mixture oxygen ozone of 30%. That means it's not an easy gas to manage. The advantage is that normally in the ozone produced and used in the labs and industrial scale, normally the percentage reaches at most 10%. That means it's not a problem. More of some ozone properties I indicate here. It's blue gas, irritant, more heavy than air. That means that it remains near the surface. This is very reactive and unstable. That means it's good, very reactive and unstable, because it reacts fast with the chemical compounds. I say before, was generated in situ. It need to be generated in situ. It's more soluble in water than oxygen. That is good in order to have the effect of oxidant. It's a strong oxidant and used as disinfectant. Advantage because it has formed by atoms of oxygen, does not introduce new ions in the medium, the water medium. This is also one disadvantage, that from a technological point of view, normally the mass transfer control the process. That means transfer the ozone from the gas phase to the liquid phase when it reacts with the pollutants in the water, mainly is the control of the global process. And I said before, it's air and toxic pollutant. And here you see some pictures, nice pictures I found on the internet about difference of ozone tropospheric, ozone stratospheric, etc. And this is also important because the toxicity of ozone to humans. That means it's not an easy gas to manage. And if you work in the lab, you have a very good ventilation in the lab, under an exhausted fan. It's not easy. If not, it's very easy. You get a cold very easy. Or you have problems of asthma, it will be increased these kind of problems. Well, this is a slide shows the relation with ozone on and the AOPs. Sometimes people indicate that ozone is an AOP, and sometimes others indicate no, ozone is different than AOP. And I suppose at the end of this webinar, you will know that it's the reality. Ozone, it's an AOP and has special characteristics that are very valuable. In this slide, I indicate all the, well, not all, I suppose there are more AOPs, but you will see the first indicated, this is first, involves ozone as AOPs. Remember that the AOPs was defined in 1987 by Will Leys regarding to the hydroxyl radical advantages in water to remove contamination, and alike condition. That means the conditions were like and always focused in the hydroxyl radical. Later on, to the investigation, other processes enter in the AOP, in the AOPs, like phenton, like photophenton, photophenton, electrochemistry process, titanium dioxide photocatalysis, and also people will know more about the AOPs, and it's not only the hydroxyl radical, other radicals, hydroperoxy, and also other radicals that make the same function as hydroxyl radical are persulfate or perosulfate enter in this plant. That means that nowadays maybe we need to talk about hot AOPs. That means AOPs that there is really not light condition. That means room temperature, atmospheric pressure in order to remove or produce hydroxyl radicals or similar radicals, and like AOPs that are the initial ones used and defined. Well, let's go to some chemical properties of ozone, and the most important is this: is the reactivity. You will see in this graph we have the ozone. The ozone may react in two ways. One way is this: it takes compounds, you oxidize the compounds, and this is the direct attack of the ozone to the organic or inorganic molecule. The advantage of this attack is on high electron density at sheets and is selective. Not all the compounds have more or less the same mechanism. And the second is through the production on hydroxyl radical. And the hydroxyl radical, it's very known, and oxidize the compound. And hydroxyl radical, it's much more inselective. It's very selective, and really few compounds resist the action of the hydroxyl radical. That means hydroxyl radical does not discriminate between one molecule or another molecule. And there are some generalistic considerations taken into account, initiators of these hydroxyl radicals, hydroxyl ions, hydrogen peroxide, UV radiation, some promoters, ozone, hydrogen peroxide, organic matter, and here it's another important thing: inhibitors. There are some inhibitors, there are some scavengers, and one scavenger is hydrogen peroxide. We will talk later about this because there is an important process, AOP process, peroxone, that means ozone with hydrogen peroxide, that is mainly used also in plants and has some this kind of controversy. Well, in the previous slide, maybe I got too fast. One important advantage of the ozone is that you may modulate, it's important to modulate the effect of the ozone in this way or in the other way. That means it's a possibility to modulate by this way, doing the oxidation selectively or doing the oxidation unselectively. One possibility is to try to make selectivity. That means destroy all the pollutants independent of the type of the pollutants. And in this case, there are some interested ozone bases AOPs that moves towards high production of radical hydroxyl. Some of them you may consider in the lab scale. If you want to move to a pilot plant scale or demonstration scale, is problematic. Mainly because I have written it in red. In red, that means to change the pH for large volumes or large fluorides, it's not easy. It's not easy. It's complicated. The same happened with the use of UVC. UVC for this reaction, you need to UVC because bubble length for the reaction is below 310 nanometers, and it's complicated. You need also quartz material that is fragile, lamps that are not reusable, etc. The ozone hydrogen peroxide, this is maybe all of this is the most used after direct ozone treatment, has this problem, the cost of storing and manipulating hydrogen peroxide. It's not very easy to manipulate hydrogen peroxide at high levels. And finally, catalytic ozonization. The same has a small problem or a moderate problem in removing the catalyst. You put a catalyst, normally it's a solid material you need to put in with the water matrix, and later on you need to remove this. That means looks not very congruent to make this. Well, hydrogen peroxide, it is the peroxone. This is the chemical reaction of the peroxone. This is not the reality because it's the stoichiometric reaction. You need to add hydrogen peroxide molecule to molecules of ozone, and you have this reaction giving two hydroxyl radicals. And it's important the ratio of the hydrogen peroxide ozone. You will see here it's 1 to 2, but really no, it's approximately small to small. Glass indicates that the best results was at most or less 1 to 1. What? Because hydrogen peroxide is also a scavenger of the hydroxyl radical that you produce. That means that in some cases, instead continuous dosing ozone to a batch reactor of wastewater, micropollutants, and hydrogen peroxide inside, maybe sometimes it's much better to dosify both at the same time. Dosify ozone, dosify hydrogen peroxide, and the results in continuous is good. And one important advancement in this area is at the end, I think maybe started, I think in the 19s, is the electroperoxone. That means hydrogen peroxide to have in storage, it needs a lot of important inversions because it's not that easy to storage as a liquid. It may explode. And how is possible to generate electrochemically? And there are some papers, nice papers lately that work on this. And this all goes in this direction. Direction I said before, direction is transfer all the oxidation power into an hydroxyl radicals that are not discriminative with the compounds to be removed. Well, another important, this is an important point also is the ozone generation. I said previously in presentation that I will talk just one slide about this because it's a problem. The generation is a problem because it's not a problem because for on-site it's not problematic. Not problematic because the technology is very easy. You only need to, as indicates it, you need a discharge at the electric. And in this discharge, you produce some radiation and also produce ozone. It's not very complicated. Unless you want to use UV radiation, but it's a very low ozone concentration, and normally it's only the labs, not in the pilot plants or demonstration scales. Here indicates some advantages of the ozone, not necessary to transport, not necessary to storage. High light is no cost, you don't pay for the use of the ice, the ice. Easy to produce, the technology is very simple, but there are some drawbacks. You need to remove the humidity, the excess of ozone has to be removed because if not, you contamine the atmosphere. And this is maybe the big drawback is only the 5% of the using electric energy goes to the tissue bonds. That means the electric yield is very low. But I know that there are some people in Japan, mainly in Japan, that is working in producing better yield for the electric to chemistry yield. Well, let's move to the wastewater treatment. In general, not necessarily by ozone. If you want to treat water and wastewater, normally it's because the objective is renewable pollutants. And in this case, there is a logistic that it depends really on the cost of the logistic, that it's first try to physical methods that are not destructive as mechanical, cementation, filtration, absorption, reverse osmosis, and later on, all try to use destructive methods that are more expensive. Chemical methods are more expensive. Chemical oxidation and reduction are expensive. Biochemical oxidation is cheaper. And at the end of the level, it's this kind of compounds that are some part costly. That means that because you use them at the end of the chain of treatment. Well, with reference to the water treatment, the ozone is very implemented nowadays in the tap water plants, the water treatment plants, and this is a very simple. It's more complex, but this is the simplest way of the use of the ozone. You have the raw water. You want drinking water. That means you have here the soil removal, coagulation, sedimentation, later generation to put ozone, later activate carbon. This part corresponds to already organic matter removal, and finally some filtration, and sometimes at the end some chlorination, and you have advanced purified water. This is very simple, but in really there are more complex than this, but it's very simple that I found in internet. In the case of wastewater treatment, it's the same. The objective is the same. The objective is to removal of pollutants. And normally the way is similar to the previous one. You have primary treatment to remove solids normally. Secondary, normally biological treatment. Here I put the typical activated sludge. Activated sludge. Nowadays it's changed by membrane bioreactors or moving bed bioreactors that are all different. And finally, a tertiary treatment that is optional, some time for chlorination. This is an easy, and important is the removal is the same, and the difference is the matrix, the water matrix, is more complex in the sewage matter that the raw matter you use in order to have water, drink water or tap water in a water plant. In order to remove the pollutants, oxidation, AOPs are not the only technology. There are other technologies that may help this part. That means adsorption processes, bright process that are used also in water plants, in wastewater plants, and also biological reactors. And here in this slide, I indicate more or less some drawbacks that has the AOPs and also biological reactors. That means you need to evaluate hazardous products that may be formed during these chemical or biochemical reactions. And another drawback, but it corresponds to the adsorption process and prior process, is that really they don't solve completely the problem. You have some contamination in the liquid, and this is a transfer of the contamination from the liquid to a solid or to a concentrate. And in the same, you need to treat the concentrate of water. It means it do not solve specifically the problem of the removal of pollutants in water or in wastewater. Well, parameters that you need to follow if you are working or researching in water and wastewater treatment by ozonation or with activated carbon or similar one. It's independent. There are many. I indicate some of them that it's interesting to follow that affects the chemical oxidation as total organic carbon, dissolved organic carbon, alkalinity. This affects a lot of the ozonation. Also affects the turbidity, also affects the nitrate content, and also the UV 254 nanometers. The turbines measured at 254 nanometers. That correspond to the aromaticity, how many aromatic compounds may I have in the water matrix. And here, yes, I put different wastewater treatment plants because the problematic of the pollutants in the wastewater is more complex than the problematic in water. Normally, when I want to produce drink water from water, they use water that has enough quality to be treated. In wastewater, the quality is so bad. Here is just more list, a list, bigger list that the parameters to follow, to control, in order to have an idea of what happened during treatment of water or wastewater. I say chemical oxygen demand. I haven't included in the previous slide. I haven't included suspended solids. I include only turbidity. I haven't included the ammonia content. That means it's nice to see because ammonia may be oxidated by ozone and other oxidants. And also in molecular analysis. Molecular analysis is very complex, and sometimes people make some groups and talk about box, PAS, pesticides, phthalates, phenols, parapharmaceuticals, etc. And here there is an important parameter that is not very much used, that is organic matter fractionation. In this case, it's liquid chromatography with organic carbon detection. This is not very new. I think it started 10 or 15 years ago. Really, it's a liquid chromatography, size exclusion, with organic carbon detection, that all the organic matter that you have in the water matrix, water or wastewater matrix, there is a separation according to the molecular weight. And here you will see some fractions interesting that you may extract for this organic matter in the water matrix. That's biopolymers, humic acids, building blocks, low molecular neutrals. And this is important because there are many people working in this field and relating this with the problems that people have in membrane separations with the fouling. And if you make oxidation treatment of the water, you oxidize the water, organic water that is in the matrix, and maybe you change the conditions, and maybe you have problems in the last part of the membrane separation you have in the last of the train of the wastewater treatment. Other important characteristics of ozonation in wastewater treatment, I think it's similar to other oxidation treatment, is this. The evolution of the contagion mineral removal. Normally, contagion removal goes this way. And other parameters at the chemical oxygen demand, total organic carbon, follow similar behavior. This is removal, the remover. And beauty change is interesting because there is an up and down. And this point is interesting because if you want to coupling chemical and biological processes. Another point important is that toxicity, I haven't indicated in this figure because toxicity, it's complicated. Sometimes increase, sometimes decrease. It's toxicity. Managing toxicity it's very complicated to make to explain a behavior. And things, the kinetics, the removal of carbon, TOC, the compound, the total carbon, COD, UVA. Normally, at first time, it's a fast reaction. A second period of slow reaction. First is fast, and later it's a slow reaction. According to the, I will say later, or time or transfer of some doses. Well, let's talk about some modeling. I know that people, when saw some equations, don't like a lot in a presentation, just to indicate that it's very important to know the mass transfer of ozone in your system. The ozone in mass transfer depend on physical properties, concentration interface, the direct turbulence, the halo gap, double side, and this is a two-field model. I suppose some of you are from chemical engineering, I suppose, and know the two-field models. That means the ozone gas needs to move to the interface needs to move to the bulk of the liquid, of the water, and reacts here. That means, and this is a kinetic step that follows equation like this, that normally, because of the low concentration in the ozone in the gas phase, the control is in the liquid. The controls the diffusion here in the small layer, and this is a typical problem of absorption with chemical reaction. There are a lot of information in the scientific literature, in general books on chemistry of this, and appears a number that has a number that many people know of this. It's It's just to know that if you have problems in mass transfer ozone, you need to move in this field. There is information about some of these parameters. By example, in the ozone mass transfer, there is a lot of information is available, mainly using water, pure water, no wastewater, and his values of KLA, this is the kinetic constant of transfer from the liquid in the ozone mass transfer. And I recommend this paper, but you move in the internet or you move in the scientific literature, you will find many correlations that are good. That means you may simulate this behavior. And the same happened with the reaction of the ozone. I indicated previously that the ozone may react of ozone by itself or may react producing hydroxyl radicals. That means this is a chemical reaction of removal contaminant, name it is. It's two reactions in parallel. One is the ozone direct attack, the second is hydroxyl attack. And in the scientific literature, you will find a lot of information about different kinetic constants for these reactions. And it's very easy. And it's interesting to take note that nowadays, I think if you look at recent publications, there are maybe some of them know about this, the quantitative structure-activity relationship. There are some estimations. I think the QSAR was firstly used to know if in a pharmacy, if a molecule may be reactive to treat this disease or not to treat the disease. And there is a protocol that is release estimation of parameters or prediction of parameters. It's possible to predict, because not all the compounds has been studied and have information in the scientific literature. And which is an estimation of the values. You may move to this paper. It's impressed. It's accepted. It's impressed. That means, and you will know more about this methodology that works fine in order to produce compounds that are not still studied. Well, if you move or you work at pilot plant, or you need to take and wastewater, a complex matrix, you need to take into care about the immediate ozone demand and the transfer of ozone dose. Instead of time, people prefer to use the transfer of ozone dose. And with this IOD is the minimum amount of ozone dose, milligrams by liter, to be transferred to have dissolved ozone in waters in a continuous flow. That means you have a continuous flow. You simply maintain the flow rate of the liquid constant. You modify the flow rate of the gas, and in the point when you detected ozone in the aqueous phase, this is the immediate ozone demand. Logically, if you are working with pure water, this value will be near zero. But if you work in wastewater, this value may be 2, 3, 4, 5, 10, until 20 milligrams per liter. That means it's the zone that the ozone is consumed by the high reactive compounds you have in the media. And it's important to take this into account if you work in water matrix that are very complex, as water. Also, I will move quite fastly in this. This is semi-continuous ozonation. It's possible to evaluate, to estimate this IOD, the constant mass transfer ozone, the constant of removal of ozone, with this simple mathematical modeling. You may find this in this paper, and this is more or less the chap of the curve we present this modeling. Here is the IOD and the start the ozone to be detected in the liquid phase. And this is the ozone gas inlet to the system. And this is the ozone to the gas outlet to the system. You inject the ozone but this way and outlet but this way. And here you have the water. Ozone concentration in liquid water is 0 at the end. And it takes sometimes, it takes some milligrams of ozone in order to appear in the water. This is another interesting parameter to use when working with wastewater effluents. Here are experimental results in my lab of estimation of AOD, these parameters in municipal wastewater effluents from different effluents. It's interesting, one of the effluents was the sludge. The sludge, it's 75% in weight of the sludge is water, and you will see the AOD is quite large. And you look at primary effluent, that is effluent that is going to enter to a secondary treatment, that means biological treatment to remove organic matter, have an important value. And if you are in a secondary effluent that leaves the secondary biological treatment or bioreactor membrane, you will see that really this value is very low. And you will see that more or less is not the same behavior that predicts this impact model, but it's not bad. More information you may find in this journal. The removal of contaminants of energy concern by ozone depends of the dose. You will see in this slide, you increase the dose, you increase the remove. Here increase the dose and increase the remove. And also important to know that the water quality parameters of COD, UV, DOC, and BOD changes. And sometimes it's important to take this into account. That means if you work in wastewater media, it's very important to follow this because there are parameters easy to follow. And also the same happened with the LCOCD. The material that it hints disappears, and the UV acids have a different behavior than the low molecular weights, the biopolymers. You will see, it's nice to see. It's nice to see what happened with this. Another point important is importance of the total transfer ozone dose in ozonation. You will see 10 milligrams per liter, 9 milligrams per liter is enough just to remove all the compounds, but you have to take into account that they depend of the values of the chemical kinetics of ozonation and the chemical kinetics of hydroxyl radical attack. According to this is a table started for this paper. It's not the same. It's something I changed just to classify the pollutants according to the kinetic constant of ozonation, chemical constants of hydroxyl radical attack, and it's possible to classify in 5 different groups that may give different behavior when you treat these compounds with ozone. Here you will see, maybe this is very clear. This corresponds to this paper. It's not mine. It's from Stoten. It's from Sweden. They compare ozonation of eperoxone in the same conditions. You will say that the difference in remover eperoxone is more efficiency, mainly because these kind of compounds are refractory to the ozonation. And if you has only ozonation, the part of hydroxyl radical production is small. And with the peroxone, you move forward the way of the ozonation attacked by hydroxyl radical, not by ozone as itself. And finally, this is the final thing that I found interesting. Really, I indicate this from the 219, but I think if you move to 217, you may find the initials application of this, how to apply from milliopollutants in wastewater ozone. And this is the kinetics. but in this case, they integrate the kinetics. And here, this is, people say, ozone exposure. This is the hydroxyl radical exposure. And it depends of the wastewater effluent mainly. That means you may to use the chemical ozone constants and the chemical hydroxyl radical constants found in the literature, and you may find these values by doing some experimentation at lab scale. And this is the case. I use acetamiprid, that is a micropollutant resistant to the refractory to the ozone treatment directly. We in different wastewater matrix, all corresponding to effluents with different. And also we see this hydroxyl radical exposure. And in this case, there are two different zones. One is before IOD, and after IOD complexed. That means the behavior is different. It's logical because in between before IOD, practically the reaction is quite fast, and before the IOD, the reactions are slower. And with the values of Tainet, is it possible to simulate what happened with other compounds that ibuprofen?
2 minutes, Prof. Santi, I'll give you 2 minutes to finalize. Our time is running out. Okay.
2 minutes, I will finish. This ibuprofen, you will see that it's good. The simulation. Here, the same situation of exposure influence of the water quality. In this case, is water and water effluent. Normally, when one is working with water effluent exposure, it's smaller than if you work in water. And I got finally to conclusions. I will be too fast. Is ozonation is able to reduce all these important parameters as COD, DOC, UVA, turbidity. Increases viewability, that it's a very good effluent. It's important to see the change in the size molecular distribution of the line matter. Ozonation process could be described by means of two-stage model based in hydroxyl radical exposure and ozone exposure. This is almost new nowadays. And finally, this knowledge is very important if you want to design ozone contactors and determination appropriate operating conditions. Well, this is my last. Slide. Just indicate some books where you may find more information about ozone, and that's all. I suppose you may have some questions. I think I finally just in time. I think it's 3 minutes to 3 o'clock. And thank you. I will put my. You will see my face now because I finished it, and I am waiting for your questions.
Thank you very much, Prof. Santi, for such a very nice presentation on water and wastewater treatment by ozonation. In the interest of time, I will recognize Alicia Garcia to ask the question. I see the hand is up.
Yes, thank you very much. First of all, thank you, Professor Santiago, for your very nice presentation. We are currently working on ozonation of cytostatic drugs following your work, well, that of Alberto Cruz Alcalde. And we were beginning our work with ozone spike. And for what I've understood here, when you work that way, is it just to eliminate that mass transfer problem and to just focus on the mechanism of reaction?
Yes, you're right. You are right. If you work, there is one part that you may work at lab scale. I put this presentation more addressed to the pilot plant scale, demonstration scale, if you want to scale up. Sometimes, if you may remove all the mass transfer, having a solution of ozone dissolved that is not completely stable, and you speak up in the solution. It's easy. In this case, you are working just with the kinetic, the chemical reaction part. Okay, it's good.
Okay, thank you very much. And a second question, when you're working with real wastewater effluents, do you see a higher impact from the organic matter contained in that secondary effluent or the inorganic anions like carbonates, nitrates, sulfates?
Carbonates increases, sulfates not, but mainly a lot in the organic matter. The organic matter that really is the matter that competes with the microbial removal. That means I present one slide that I indicate. I don't remember the number, but you will see that, for example, the ultraviolet absorbance drops quite fast at the first times. This is very easy to follow, and this indicates what it works. There is a non-removal. There is a transformation of organic compounds in other kind of organic compounds that don't absorb the radiation.
Okay, well, thank you very much once again for your very nice presentation.
Okay, thank you to you for your question.
Okay, thank you very much. I will recognize Tizao. I see your hand.
Hello, Tizao.
Hi, Santi, how are you?
Fine, confined in Barcelona area.
Okay, thanks for the nice talk. It's a really nice presentation. I'm not sure if it's simple or complicated question. How do you see the future of ozone in the water and wastewater industry?
I think it has a very good potential. The main drawback now is the production of ozone. That means the installation is very easy. There is no technological problems. The problem is the efficiency. It's a 5% of the efficiency of the electric energy into ozone bond. It's the main problem. And the main advantage of the ozonation is that ozone, you don't need to store. The only thing you need is to use the needed that you need. That means not to produce a lot of ozone, only the ozone that is needed to remove the contamination. And not need to store. If you want to remove by using hydrogen peroxide or phantom, you will have, by example, the problem of the sludge. You will have the problem of the hydrogen peroxide also. How to manage this? Okay.
Yes. Yeah. Okay. Thanks.
Okay. Thank you very much. I will recognize Francisca. I see the hand is up.
Can you hear me? Okay.
Yes.
Yes.
I am able.
Thank you for the very nice presentation. And I would like just to ask you, I know that my question is not about the ozone treatment for water, but I would like to ask an opinion about the use of ozone, for example, to treat solids like sludges in the wastewater treatment plants, to improve, for example, the biogas production or
I know.
I don't know how is your opinion, if this is an efficient way.
I think I read, I think it was a paper, but it was 5 years ago, 10 years ago, about some people that in order to reduce the slash, the volume of the slash, and also it's possible to recover more methane, ethane, and gases and things like this. I think it's good. It's good. The problem is that the alternative of this is a biological treatment in order to have the same effect. And I'm fighting chemical oxidation with biological oxidation. It's very difficult. There is one example, but it happens maybe in the 1970s. In the 1970s, people, when they want to treat wastewater, in Barcelona, they mounted 2 plants. One plant was biological, the other plant was chemistry. They don't use biological part. They only use cal. They treat with calcium carbonate.
Okay.
And at the end, they remove the chemical plant, and the biological plant remains and great. It's difficult. It's difficult because if some microorganism is formed that may attack this specific pollutant, it's not only cheaper, it's cheaper. But ozone has a lot of potential.
Okay, thank you very much.
You're welcome.
Thank you very much. And for me, I have one question for you, Prof. I would like to find out what will be the effect of ozone on water hardness? Can you remove water hardness by using ozone?
You say photon hardness, that means calcium, magnesium, and these compounds.
Yes.
This is by coagulation. This is a phenomenon by coagulation. It's possible. It's possible. I think in the books that I indicate in the last slide, there is information about this, because if helps, there is no coagulation. It helps the coagulation. It's different, but it works. And sometimes people use the ozonation not only to remove the contamination directly by chemicalization. One part is possible to use to help to a better coagulation.
Okay, thank you very much for that.
Okay. You're welcome, and thank you to you for your good management.
I will recognize Professor Rizzo. I think this will be the last question in the interest of time.
Yes, I have time. Hi, Luigi. Oh, no, the microphone.
Yeah, can you hear me?
Yes, now see.
Yeah. Oh, thank you for your nice presentation. It's always a pleasure to listen you about this topic. I just a question about what is the situation right now in Catalonia and in Spain in terms of advanced treatment of urban wastewater. I mean, there are some wastewater treatment plants that are going to be upgraded with advanced treatment for the removal of contaminants of emerging concern, or not? Not yet.
Not yet. There are some studies, because I participate in some program, national programs, that work is in this way. But they are working in this way. But in the advanced treatment, the importance movement are in the way of membrane separations, more than in chemical oxidation to remove pollutants.
Okay, thank you.
Okay, thank you very much. And we conclude this webinar by just recapping some of the points that Prof has given us. He has touched on a lot of issues on ozone, starting from the ozone structure to its chemistry, its activation, application in wastewater treatment. He touched on current available technologies to remove pollutants from water, the important parameters to consider, LC-OCD analysis, OND, UV, VIS analysis, modeling of ozone mass transfer, and chemical reactions. He also touched on immediate ozone demand, and transferred ozone dose, and then some examples on removal of different contaminants by ozone, including contaminants of emerging concern and micropollutants removal from water and wastewater. That was a very exciting and inciting presentation. Thank you very much for giving us that insight into the application and possible treatment of water and wastewater using ozonation. It was a pleasure listening to your talk. Thank you very much.
For me, it has been a pleasure to participate in this webinar. I think it's a very good way in order to spread the knowledge of the International PhD School of Association Processes. Okay, thank you.
All right. If you need to,
I would like just to thank also Alex for organizing the webinar. Thank you for your support, Alex. Okay.
Thank you very much. If you need to contact Professor Santi, I think his email address is available on the invite PPT file. You can always get in touch with him for further discussions. Keep
please,
well,
Alex,
everyone.
when as you can, please send me the link to the registration of the webinar so I can disseminate. Okay.
Okay. Thank you very much. I'll do that.
Thank you. Bye bye.
Hey,
Bye. Keep well, everyone. Okay. Bye. All right.